Welcome to JACS in Conversation. It's my great honor and pleasure today to welcome Professor Roald Hoffman of Cornell University. He's the Frank T. Rhodes Professor of Humane Letters, well known not only as a highly accomplished scientist with over 650 publications, but also a playwright and a poet, 8 poetry books to his name, and 3 books. There's also a TV program in course. So it's tough to make a brief introduction here, but I want to leave as much time as possible so that we can hear what Professor Hoffman has to say. He was born in 1937. At that time, it was Poland. Today, it's in the Ukraine. And he and his family survived the Holocaust. He arrived in 1949 in the USA. He obtained a bachelor's degree from Columbia University, if I remember correctly. And that was followed by a doctoral degree under the direction of Bill Lipscomb and Martin Guterman at Harvard University. He has quite a history. He spent some time at the National Bureau of Standards, at Brookhaven National Labs. He was brought back to Harvard in 1962 as a junior fellow, which, if I understand correctly, was a position that's basically you're independent and allowed to work entirely on your own. And it's during that time that he worked on the theory of concerted reactions. That's, of course, what earned him the Nobel Prize in chemistry in 1981. He works on the electronic structure of stable and unstable molecules to probe their structure and their reactivity, and the periodic table is his domain, all of it, without exception. He self-describes as an applied theoretical chemist. Without further ado, Roald, welcome to JACS in Conversation. I've been looking forward to this interview.
I'm so glad to talk to you. Let me just say that scientists think they can escape the world, but they can't. And you and I are good examples of this. We were born in different places, I in Poland and you in Cuba. And we were both immigrants in the United States. And it was the United States that gave us the opportunity to do the work that we did. I'm very glad to be where I am and to be able to talk to you. And of those 650 papers, I haven't counted them up, but a very good number were published in JACS. So it is to JACS and the forum that it provided for my science that from the first Woodward and Hoffman papers, it was a part of the way I talk to other scientists. So it's very important.
Let me go back to one of your poems called Theoretical Chemistry. There's a line in there that I recall that there are multiple pathways, even though you're told there's only one. So with that as a basis, what do you think was critical to your highly successful career?
So I came to chemistry late. I did not finally make up my mind to become a chemist until 3/4 of a way through my PhD in chemistry, as you mentioned, with Lipscomb and Guterman. I think what made my path possible and easy and fruitful was that I was able to look at different parts of chemistry and to learn from each, but then to be able to let go and to go on to something else. And it was the setting of an American research institution and the freedom to do the work that allowed me to move from inorganic boron chemistry with Lipscomb to the organic chemistry that I just drank in when I worked with Woodward, and then on to organometallic, inorganic, and then solid state chemistry and the borderline with physics. Each time I sort of followed my nose, but I was lucky enough to have that opportunity. And somehow I had the fortune of of getting interested in the next molecule that I saw in JACS or in angewandte chemie. But it was that willingness to take on something new that I think that made it possible.
I'm curious
Yes.
who your mentors were, and how they were critical to your highly successful career.
I think the first people I would identify as mentors were Lipscomb and Guterman, my PhD advisors. With Martin Guterman, I started and then switched over to Lipscomb. From Guterman, I took away a love for symmetry, and Lipscomb for chemical complexity. You know, Eric, after seeing the three-dimensional character of B10H14 and the beauty of the icosahedron of B12H12 2 minus, first of all, the complexity of organic molecules was nothing to me. I had seen boron hydrides, and the bonding in them was more complicated too. So it was easy to take in organic chemistry. The flexibility, the seeing that my colleagues in organic chemistry could make anything under the sun, that's your business, that they could make little modification. If I, as a theoretician, said that if you put a chlorine group there or a nitro group there, that you will modify this property or stabilize that molecule, that was a wonderful freedom, which wasn't there in the boron hydrides because the synthetic capabilities are not there. They're still not there. And that's inherent in bond strengths, in barriers to reactions, in kinetic thermodynamic stability. But organic chemistry was wonderful.
So I'm curious, as a teacher, as a scientist, as a mentor, what do you think are your greatest hits?
So I'm glad that you mentioned as a teacher, because that is the primary factor which is not very explicit in my life. And an interesting aspect of that is that through having to teach introductory chemistry, to which my chairman of my department assigned me, and I didn't want to do at Cornell when I first came. But I was a good boy. I taught that general chemistry course. I designed a new one. It is only in teaching introductory chemistry that I learned how to explain simple ideas to people without the crutch of mathematics. So for instance, I had gotten an A+ in a thermodynamics course, but I really didn't understand thermodynamics until I had to teach it without all those partial derivatives. Beautiful mathematical structure, but also underneath it, something of great practical interest from steam engines on. It took me but a little jump to realize that when I was trying to teach an intelligent organometallic student about the orbitals in bis-cyclopentadienyl titanium, that I was just dealing with a different audience, but I had the same problem, how to explain that without writing out all the apparatus of perturbation theory and the calculations. I had to explain it in words and pictures, and I mastered that. And I think that is the key to my success. And I think it's still also the thing that I'm most proud of, that is that I've left chemists, organic and inorganic, with an orbital intuition to attach to the intuition of structures and steric situations that they normally use, all the soft reasoning, which I love, which they normally use in explaining things, not in calculating them. I know they can calculate those things. Any number you want in the world, you can get. That's not the same thing as understanding something. That's not the same thing as teaching something to someone. And it's that which I think has been really fun for me.
What about explaining chemistry to non-chemists? How do you manage that?
It's very hard. And I don't think I've succeeded till this time in explaining chemistry to non-chemists. I have tried in various ways. We made a series of films about chemistry, The World of Chemistry, 26 half hours for PBS about 30 years ago. To this day, this remains the only set of such films, though other things have come along, for instance, like the wonderful periodic table videos of Martin Polyakov, and Brady Haran, which are just wonderful images of chemistry to people. But even to this day, living in a retirement community, I am faced with a discussion: should we abandon weed killers? Okay, a simple discussion, but the discussion is phrased in terms: should we stop using chemicals?
Yeah.
That's the words used, and instead use organic ways to control the weeds. Well, in just those two sentences, there is so much chemistry to be taught, and I will do it. I will do it in a seminar in our retirement community. But here I am at 84, still explaining chemistry.
And I guess that my next question would be, how do you stay passionate about science over the course of a lifetime, right? And I guess that's the answer, right? You stay engaged with individuals who are asking fundamental questions, and you try to speak to their curiosity.
Yes, I want them to understand. I want them to know. I stay engaged, though my problem now at my age realistically is something else, and that is how to slow down and how to some measure, not to disengage, but to act appropriately to my age and what my body tells me I can do. But I stay engaged because I opened that issue of JACS and I see something interesting there. So that's really how I stay engaged. I somehow am still interested if someone makes a new molecule or has a new way of making a molecule, even if I haven't predicted it.
How would you describe yourself as an advisor, as a mentor?
Well, you'll have to ask my students, the people I've worked with. One thing we structured, and which is a hidden, in part a hidden strength of the American educational system, is the scientific family structure of a research group meeting. In our case, run quite informally. Now, I had the luxury of doing that because my group never exceeded 10 people. Okay, but at that meeting, which for us ran once or twice a week for 2 or 3 hours, everything was there. It's where the graduate students and postdoc learn that mistakes get made on evaluation. They could see what makes for good science. They could see the excitement that something new generates. They would present their talks and we'd criticize them. We had no structure. Some groups that are very large have to have a structure when they have a group meeting. But I think that informal structure was very important. And that is, keeping that up over the years, I would view the most important part of my mentorship of graduate students and postdocs. But I remember every one of them. I have really learned a lot from my postdocs. I think of certain areas in recent times that I've gotten into, like singlet fission in chemical physics, physical chemistry, or the transport of electricity across single molecules, and also superconductors and this, in general, the whole field of high pressure science. I could not have imagined, Eric, even 20 years ago, that I would be working in these areas. They were brought to me by the postdocs. And now, it's true, I had to give them the time to tell me something, and I had to listen to them. I had to give them the opportunity, but they got me interested.
So what's your advice for a young scientist seeking a career in science today? How would you advise them to craft their own story as a scientist?
I think to have some faith in yourself that whatever you're interested in will turn out to be, in the end, interesting to other people as well. But on the way to doing that, there has to be a curiosity. There has to be a willingness to, or a desire to see the connection of anything to everything else.
If I could switch to some questions about JACS. What's your favorite JACS publication emanating from your group, if there is one?
I have to think. So the most influential ones were, of course, the ones with Woodward. But actually, that's, as for JACS, I'll pick a more recent one. That's because I don't live in the past. Oh, that was wonderful work. And incidentally, Jeff Seaman, in a series of 27 remarkable articles, is tracing the history of the development of the orbital symmetry rules. They're getting published in another journal. They're quite amazing. And a large part of it comes from the notebooks that I kept in that period. I stopped keeping notebooks after a while, but at that time I kept those large Urim and Peace wonderful notebooks where I kept notes of what I was doing. I would pick actually a recent paper I did with an Indian postdoc, Priya Kumari, who is now an assistant professor in India. And it was about designing some new compounds, which I can explain to you or to a chemist pretty easily. And they were things which had an aromatic nucleus, and then let's say there were two methyl groups, so that you have the xylenes, and then you replaced the carbon by either P plus or by boron minus. So you got a dication or a dianion. These were isosteres, as Langmuir would call them. They had the shape of the xylene, but they had some other substituents and a charge. And we tried to design some of these, and we found that some of these should be stable. And what I like about this paper is, I'll tell you what we did in it. We found that these molecules did not have the kinetic persistence that we had imagined for most of them. We had imagined they would be stable, but in fact, they rearranged in no less than 4 different ways to escape those charged Lewis structures that we had created that I could explain in a flash. And we examined those. And I think what we did, so why do I like this paper? It's a small paper, but you can ask the then editor for theoretical chemistry, who was Wes Borden. And as it happened, it's the only paper in 19 years that he ever got 3 comments to publish without any change on. Okay, so I had crafted it well. Now, it was also the only paper I have ever published where that has happened, except for the papers with Woodward that didn't get reviewed, period. But all my papers had the benefit or the agony created by referee comments. But the reason this paper was good was that I was showing by example to, I didn't say it in a paper, but I was showing other theoretical chemists that when you suggest a novel molecule, these were those dications and dianions, that what you must do is examine all the ways that the real world molecule can escape that geometry and that situation that you put in. So we examined 3 or 4 alternative routes, actually calculating activation energies, which we could do now, which I couldn't do in the Woodward days. And I think by writing this article, I set an example for other theoreticians for what you should do when you suggest a new molecule. So
How
that's
do you
why
know when you've captured all the pathways? How do you know if you haven't missed a pathway?
Yeah, I have. So, okay, you know the answer, Eric. If you can't think of it, the referees will. Okay, first answer. Second answer is structure your research group meetings, which we did, so that that at some point you break the meeting and you have 5 minutes for everyone to suggest how the molecule can escape that. And every person has a different background, but they can they can respond to that. So structure it so that you have a system for evaluating. Good question.
What can JACS do better in this new century? And what has JACS done well?
I think JACS can do better. JACS has become stodgy. And my own answer is not going to please ACS publications, nor some other people. I think the world is more than chemistry. We need to see chemistry in society, and we don't see it in JACS. Putting it into the journal, to me, emphasizes the importance of those things. What JACS has done well is expert refereeing, reviewing, in choosing the sub-editors and the sub-editors choosing the reviewers to review the papers very well and with a proper degree of skepticism, which has to be there. It has not done so well on sort of conceptual theoretical papers, the ones which are less straight computational chemistry. And it never did very well on physical chemistry, chemical physics, and or at least some parts of it. Okay, so JACS can't do everything, but it I think could do somewhat better on a physical chemistry. I think it does well in having the articles be as readable as scientific papers can be. The editors, but it's the editing that really is very good.
So we're taking some of these suggestions to heart. I'm working on bringing in more associate editors in physical chemistry to be more inclusive, as it should be, given that it's the flagship journal that attempts to cover as much of chemistry as possible of the American Chemical Society. Let me take this opportunity to warmly thank you for this wonderful conversation we've had. Hopefully not the last that we'll have. And wish you all the best. I remember hearing you talk about 5 years ago, chemistry at high pressure.
Yes.
I think it was in Belgium. Fascinating. The kinds of molecules that one can Well, that one doesn't imagine until one starts to consider the conditions of high pressure in the Earth's mantle. And it's amazing, right?
Yes, that world is still waiting to be explored. We need to return to high pressure or learn how to do chemical reactions at high pressure. One of the things you can imagine that's a problem at high pressure is just to mix the chemicals so there's contact, because they're frozen in place. So that's it's a general problem of why chemical industry does not generally work in a solid state. It prefers liquids solutions often, or gas phase will do, except gas phase doesn't put through much stuff. So liquids for both biology and the chemical industry are the place to run reactions.
Thank you for joining us at JACS in Conversation.